today's topic is limitations of valence bond theory and origin of molecular orbital theory. Because there are some limitation to the theory, then next theory comes into picture. So what is valence bond theory? According to valence bond theory, valence electrons participate in the bonding. Only valence electrons. They will attract with the nuclei, they will repel each other, but there is no case, there is no study, and there is no discussion about the inner electrons. In valence bond theory, as the name suggests, according to valence bond theory, only valence electrons and nuclei, they will interact. But it is not the case actually. All the electrons belonging to one atom interact with the other atom. Okay, so that is not discussed in valence bond theory. So this is the first limitation of valence bond theory, right? That only valence electrons are discussed while forming bond. Second, O2 molecule. So O2 molecule has unpaired electrons, but it is not explained by valence bond theory. According to valence bond theory, if one oxygen interact with other oxygen, there is pairing of electrons. It is like this. There is pairing of electrons. But actually, according to molecular orbital theory, it has unpaired electrons, and the one which has unpaired electrons, don't write it like this. O2 molecule has unpaired electrons. It is according to valence bond theory, okay? So it was not explained by valence bond theory. According to valence bond theory, O2 has no unpaired electron. There is pairing of electrons, right? So valence bond theory cannot explain it. And the one which has unpaired electrons are called paramagnetic. And this paramagnetic means, see, paramagnetic means the substance which is attracted by the magnet. Paramagnetic substances. The molecule, atom, ion, any solid random substances, the substances which have unpaired electrons and are attracted by, is it visible? Magnetic field. That is attracted by magnetic field, right? That means O2 has unpaired electrons, so O2 is paramagnetic, and second is diamagnetic substances. Diamagnetic substance. The substance which has, or we can say substances which have paired electrons. And are weakly repelled by magnetic field are called diamagnetic substances. So O2 is paramagnetic in actual. O2 has unpaired electron, so O2 is paramagnetic. But valence bond theory will not explain this thing. Okay? So this is the biggest challenge to valence bond theory. That why if O2 is paramagnetic, it should be explained by valence bond theory. That means valence bond theory needs some modification. Pair of electrons and unpaired pair of electrons. Unpaired, no, sorry, you are confused. All metals are, most of the metals are paramagnetic. Okay, Subhajri Pothal, good evening. Namita, good evening. Ralam, see, if like sodium, it has one unpaired electron, so it is paramagnetic. Okay, but if we talk about beryllium, right? So beryllium has paired electron. Okay, got it? Now you are talking about lone pair and unpaired. Lone pair means unshared pair of electrons, and unpaired electron means unshared electron. One is pair, other is single. Like ammonia. Ammonia has unshared pair of electrons. Unshared pair of electron, and that is called lone pair. Right? But NO2, this is unpaired electron, that is also called lone electron, not lone pair. Okay, Tanya ji, good evening. Got it? Okay, very good. Then third limitation. First limitation is it takes into account only valence electrons. Okay. Second limitation, it could not explain the paramagnetic behavior of O2. Third limitation, canonical structure or resonating structures are drawn to explain properties of certain molecules, none of them is actual structure of molecule, resonance hybrid is a real structure of molecule. So resonance is also an uncertain type of bonding, right? In resonance there is a partial double bond character, so that is also not explained in valence bond theory, because in valence bond theory there is either single bond, double bond or triple bond. Okay, there is no space for the fractional bond order in valence bond theory. Okay, so resonance is also a limitation of valence bond theory, where a single structure cannot explain the properties of the molecule, all the properties of the molecule. There are limitations of valence bond theory, but shapes and geometry of the molecules, covalent molecules, can be explained successfully by valence bond theory. Though it has limitations, but shape of the molecule, arrangement of the bonds, that is successfully explained by valence bond theory. And to get rid of, to remove these limitations, there is the other theory which was given by Hunt and Mulliken in 1932, that is called molecular orbital theory. This theory was given by Hunt and Mulliken, and that is called molecular orbital theory. So say, atom and molecule, the basic difference between these two terms, if anyone asks, you say molecule is combination of atoms. Am I right? If anyone asks you what is molecule, you always reply like molecule is combination of atoms. Am I right? So now we will go dig into the matter that what is atom. Atom has actually atomic orbitals. Atom has atomic orbitals. In terms of, because we are dealing with molecular orbital theory, right? So atom has atomic orbitals. On the same line, when molecule is formed, there is combination of atoms. So molecule has molecular orbital. Atom has atomic orbital, molecule has molecular orbital. Now, atomic orbital has a single center. That is, in an atom there is only one nuclei. In atom there is one nuclei, means it is monocentric. All atomic orbitals has common center, that is nuclei. Okay, there is single nuclei. But in molecular orbitals, in molecule, there are many atoms, maybe 2, 3, 4, depending upon, like if we talk about oxygen, so O2, that is diatomic, means that molecular orbital is under the influence of 2 nuclei. Now let us take example ammonia. So in O2 it is dicentric, molecular orbital has 2 centers. It is in connection with two nuclei. But if we talk about ammonia, ammonia has 4 atoms, so it is tetracentric. That means molecular orbitals are polycentric, depending upon the combining nuclei. Okay, it is under the influence of single nuclei, they are under the influence of combination of nuclei. So if we define what is atomic orbital, tell me. The region in space around the nucleus where the probability of finding, or we can say probability density, okay, probability of finding the electron density is maximum, right? The probability of finding the electron density is maximum. Now tell me about molecular orbital. The region in space, which space? Comprising of combining nuclei, region in space comprising the combining nuclei around which, say, there is maximum probability of finding electron density. So difference is, this is around the nucleus, but here space comprising the combining nuclei around which there is maximum probability of finding the electron density. So that is the difference between atomic orbital and molecular orbital. Means atomic orbital is under the influence of one nucleus only, but molecular orbital is under the influence of many nuclei, depending upon the number of atoms present in the molecule. Because see, space comprising of combining nuclei. Okay. Now the formation of molecular orbital can be explained, right? LCAO, formation of molecular orbitals can be explained by the principle called linear combination of atomic orbitals. It is linear combination of atomic orbitals. Linear combination of atomic orbitals. Now what is this linear combination of atomic orbitals? Means there is addition or subtraction of wave functions, or we can say electron waves, when two types of molecular orbitals are formed. See, if we have two atomic orbitals, when they combine, we get two molecular orbitals. See, number of atomic orbitals combining together is equal to number of molecular orbitals formed. Got it? Atomic orbitals doesn't mean they will merge together. When two atomic orbitals combine, we get two molecular orbitals. Okay? And you know, actual atomic orbital means there is electron wave. Electron behaves as a wave. So wave is either in phase or out of phase. In phase and out of phase. See, combination of atomic orbitals is of two types, either addition or subtraction. Let us take psi A as the wave function of atom A. This wave function means atomic orbital of atom A. Atomic orbital of atom A. And psi B as wave function of atom B. Right? So when these two wave functions, or we can say two atomic orbitals interact, or two electron waves interact. See, wave function or atomic orbitals or electron waves. See, in three types I am calling it: wave function or atomic orbitals. Wave function is actually atomic orbital, and in atomic orbital there are electrons, so that is called electron waves. So in wave, you know, there is what is this? Wave has two parts. This part is called, this plus part is called crest. Okay? And negative part is called, can I write here? I can write here, trough. Okay? Very good. So these are not actually signs. Sorry, these are not actually charges. These are the sign of the wave function. What are these? Sign of wave function. If sign of the wave function is plus, that means crest of the wave, crest of the electron wave. Or if negative sign is there, that is trough of the electron wave. So if question is what is the significance of plus and minus signs, so keep in mind, plus sign is means crest of the electron wave, and minus sign means trough of the electron wave. Okay, I can write plus sign means crest of the wave, electron wave, and minus sign means trough of the electron wave, right? So when two electron waves combine, so first, if they combine by addition, so see, if addition is there, we get bonding molecular orbital. Addition gives us bonding molecular orbital, and it means psi bonding, that is equal to psi A plus psi B. That means there is addition. Addition means waves are in phase. Addition of wave function gives bonding molecular orbital. That means waves are in phase. In phase means crest over crest and trough over trough. See, I can write here. Crest over crest, trough over trough. There is no phase difference. So when they combine, that is bonding molecular orbital, that is psi A plus psi B. This is psi A and this is psi B. Okay, so bonding molecular orbital is formed and it is like this. That is addition of wave function and that is called bonding molecular orbital. Okay. Now, after forming this bonding molecular orbital, now antibonding molecular orbital. In antibonding, there is subtraction of wave function. That means waves are out of phase. Waves are out of phase. That means here antibonding is represented by psi star and that is equal to psi A minus psi B. That means in this case, is it visible? Yes. There is crust over trough and trough over crust. This should be equal in size. Is it visible? Yes. Yes. If no, crust over crust means there is addition. Trough over trough means addition. So it becomes larger in size. If crust over trough, trough over crust, then there is a decrease in the amplitude. There is a decrease in amplitude. Okay. So in this case, there is subtraction of wave function and amplitude decreases. Okay? Yes, crust over crust means addition. Trough over trough means addition. But crust over trough or trough over crust means subtraction. Okay? So this is called linear combination of atomic orbital. Okay? Now, what is psi square? Psi, you know, that is the amplitude of the wave. Psi is amplitude of the wave. Psi is actually amplitude of wave. Means height of crust or depth of trough, right? Psi square represent probability of finding the electron between the combining atomic orbitals, between them. Okay, so psi bonding sphere equal to psi A plus psi B whole square. So it becomes psi A square plus psi B square plus 2 psi A psi B. But in psi star, this is psi A minus psi B whole square. It becomes psi A square plus psi B square minus. So tell me, if we have two atoms, okay, bonding molecular orbital, anti-bonding molecular orbital, means psi B and psi star. So tell me, these are nuclei, okay? So in between the nuclei, electron density in bonding, electron density between them is more, because it is psi A square plus psi B square plus 2 psi A psi B, increased by this amount. But if there is anti-bonding, electron density is decreasing. So that means in this case, these electrons in between the nuclei, they shield each other. So repulsion between the nuclei decreases because they are involved in attraction with the electrons in between the nuclei. But here it becomes thinner, electron density decreases by this amount. So now nuclei are feeling more repelled than before. When they combine, there is more repulsion between the nuclei. So tell me, out of bonding and anti-bonding, which one has higher energy? Anti-bonding molecular orbital. Anti-bonding molecular orbital. Why is it so? Because in anti-bonding, repulsions are more. In bonding, attractions are more. So because of attraction, energy is released. And because of repulsions, energy is absorbed. Very good. So anti-bondings are less stable, bonding are more stable. So say, when we have this is psi A, atomic orbital belongs to A atom, psi B, atomic orbital belongs to B atom. This is about A atom, this is about B atom, now AB. When these two atomic orbitals belonging to different atoms combine, we get two molecular orbitals. One is below these two and one is above. So this is anti-bonding and this is bonding. This is psi A plus psi B and this is psi A minus psi B. Bonding, anti-bonding. So this is energy level diagram actually. If energy of atomic orbital of A and atomic orbital of B is on this line, then for bonding molecular orbital energy is less than any of the atomic orbitals, and for antibonding energy is more than any of the atomic orbital. Now let us do some other questions like difference between atomic orbital and molecular orbital. Okay. Write difference between atomic orbital and molecular orbital. So write the difference. In this atomic orbital, the electron cloud extends around the single nucleus. Because in atomic orbital, the whole electron cloud is belonging to or is under the influence of single nucleus. In molecular orbitals, the electron cloud extends. Is it visible? Yes. The electron cloud extends around the nuclei of bonded atoms in the molecule. So that is the first difference. Okay, that atomic orbital is in atomic orbital electron cloud is extending around the single nuclei. Okay, single nucleus, but in molecular orbitals electron cloud extends around the all nuclei which are involved in molecule formation. Okay. Second, it is monocentric in nature and molecular orbital it is polycentric in nature. Visible? Yes, very good. So atomic orbital, it is the property of single atom only. And it is the property of combining atoms of the molecule. Yes. Have you written any? No, it's not like that. Atomic orbital is stable, molecular orbital may be stable or more stable or less stable. See, bonding molecular orbital is more stable than any of the atomic orbital, and anti-bonding molecular orbital is less stable than any of the atomic orbital. So we can't write that a molecular orbital is less stable. It may be more stable. Okay? its shape is simple. You know, S, P, D, F. S is spherically symmetrical, P is dumbbell, D is double dumbbell. Okay, but molecular orbital, its shape is complex in nature. I can write below, yes. Atomic orbitals are designated as sigma, pi, delta. I let you know what is sigma, pi, delta, but molecular orbitals are designated as sigma star, pi star, delta star, etc. Okay, so these are the basic differences between atomic orbitals and molecular orbitals. Difference between bonding molecular orbital and anti-bonding molecular orbital. A bonding molecular orbital you should write in full. Bonding molecular orbital. Don't write BMO. Just write complete bonding, then molecular, then orbital. Okay? A bonding molecular orbital is formed by the linear combination of atomic orbitals. By the linear combination of atomic orbitals. Write full. Linear combination of atomic orbitals. Okay, when their wave functions are yes, bonding of molecular orbitals are formed by the linear combination of atomic orbitals when their wave functions are added. And what about anti-bonding? Anti-bonding, I write AB, sorry. Okay, a bonding molecular orbital, okay. But okay, bonding molecular orbital is formed by the linear combination of atomic orbitals when their wave functions are added. Here, anti-bonding molecular orbitals is formed by the linear combination of atomic orbitals when their wave functions are subtracted. Right? When addition takes place, you know, if we have p orbital like this, so plus crust and crust, then that is called bonding. If I write it like plus minus, crust over trough, same sign, okay, then it is called bonding. If there are opposite sign, that is called anti-bonding. Right? So second point is, it is formed when the lobes, these are called lobes, say, this is positive plus lobe, this is negative lobe. These are called lobes. What we call them? Lobes. Okay? So it is formed when the combining atomic orbitals have same sign. That means plus and plus or minus and minus. We have written just now. Crust over crust, trough over trough. If it is opposite, that is antibonding. Yes, tell me. So antibonding molecular orbital, it is formed when the lobes of the combining atomic orbitals have opposite sign. That is plus and minus or minus and plus. Right? What about that only Ralam is writing? Just go on writing. What about energy? Yes, now tell me. I will ask now. What about energy? Energy of bonding molecular orbital is less than atomic orbitals or more than? Its energy is less than that of combining atomic orbitals. And what about this? Its energy is more than that of combining atomic orbitals. What about electron density between the combining nuclei? In bonding molecular orbital, electron density. Tell me about electron density. Yes. Yes. Electron density between the combining atomic orbitals increases or decreases? Is more or less? Very good. In bonding molecular orbital has higher electron density and atomic or say where more between the nuclei, okay? Means it is outside the nuclei, okay? Very good. It increases electron density between electron density, the space between the nuclei, between the nuclei of the atomic combining atomic orbitals. Or we can say combining atoms. That is nuclei are, can I write below it? Yes, nuclei are shielded. In this case, nuclei are shielded, right? But here it decreases. It decreases instead of increases. Now it becomes decreases electron density in the space between the nuclei of the combining atoms, that is nuclei are de-shielded, because now there is more repulsion between the nuclei. Here repulsion between the nuclei decreases, because between the nuclei electron density increases. That becomes a shield between them. Okay, so repulsion between the nuclei is less here, but repulsion between the nuclei is more in this case. Point number 5. It stabilizes the molecule and favors the formation of bond, because as repulsions are decreasing, that means electron density between the nuclei increases, so it stabilizes because energy is less, so it stabilizes the molecule and favors the formation of bond. Okay, but here instead of stabilizes, as it increases energy, so it destabilizes the molecule and against the formation of bond. It is against the formation of bond. Yes, very good. Now, bonding can be represented as sigma pi delta. Okay, but this is 5th. It can be represented as sigma star, pi star and delta star. Oh, sorry. In case of atomic orbitals, I have written like sigma, I think so. So please change it. In atomic and molecular orbital, I think I have written like this only. In atomic orbitals, it can be designated as S, P, D and F. Okay, and molecular orbital, that can be represented as sigma star, pi star, delta star. Please change that last point. In atomic orbital and molecular orbital, I have written, I think it can be designated as the sigma pi delta, sigma star, pi star, delta star. I have mixed bonding and anti-bonding actually. So in atomic orbitals, S, P, D, F, these are the atomic orbitals. So it can be designated as S, P, D and F, and molecular orbital, these. Without star are bonding and with star are anti-bonding. Okay, good night Abhijit.